Hello everyone. Today, I'm honored to introduce our work, AdaCluster. The full name is Adaptive Curl Key Clustering for Sparse Attention in Video Generation. This is a joint research project from the University of Science and Technology of China, the University of Macau, and the Chinese University of Hong Kong, and our work will be presented at CVPR 2026. Our research focuses on major efficiency problem in video DITs. We propose a training-free adaptive sparse attention framework to solve this critical inference bottleneck. First, let's talk about the background and motivation. Recently, video DITs have reached state-of-the-art performance on video generation texts. However, they suffer from extremely slow inference speed. The main reason is the correct complexity of self-attention. As video resolution gets higher and the sequence length becomes longer, the computation cost of attention rises sharply. In most cases, attention calculation takes up more than 80% of the total running time. This greatly limits the real-world application of high-resolution and long video generation. As video resolution gets higher and sequence length becomes longer, the computation cost of attention rises sharply. In most cases, attention calculation takes up more than 80% of the total running time. This greatly limits the real-world application of high-resolution and long video generation. Besides, current sparse attention methods still have two obvious drawbacks. First is the static clustering with a fixed pattern. It ignores the different feature distributions across transformer layers. Fixed clustering settings can't balance compression rate and video generation quality. Second is the selection bias from cluster centers. Traditional methods easily miss important semantic tokens near cluster boundaries, which causes visual problems such as blurry details and unstable frame changes in generated videos. To solve these two key issues, we put forward AdaCluster. It's a training-free, adaptive curl key clustering framework for video generation. Our goal is to greatly boost inference speed, with almost no loss in video quality. Next, I will introduce our core methods and key innovations. Our design has two core ideas, adaptive clustering and accurate critical token preservation, with three key functional modules. The first one is angle similarity guided curl clustering. Original curl vectors have huge differences in value magnitude, so using Euclidean distance for clustering cannot reflect real semantic similarity. To fix this, we normalize all curls to a unique sphere. In this way, semantic similarity is determined by angular distance. This clustering method supports higher compression and makes sure semantically similar curls are grouped reasonably. The second part is layer-wise adaptive dynamic key clustering. Key features change a lot in different network layers. Low layers focuses on texture information, while high layers capture advanced semantic features. Fixed cluster numbers can't fix this characteristic. Therefore, we adjust the cluster quantity dynamically for every single layer. We recluster outlier tokens to make feature grouping more compact. Meanwhile, we set an upper limit for cluster numbers in higher layers to avoid overcompression and keep full attention when needed. We also reuse cluster centers from the previous layer, which largely reduces extra computation cost. Third, we design an efficient token selection module called TensorQuest. Clustering brings new costs for finding critical attention tokens. To improve efficiency, we propose TensorQuest. Different from ordinary CUDA core calculation, this method makes full use of GPU tensor cores. We split curl vectors into positive and negative parts and convert matching operations into optimized matrix multiplication. This design makes critical token selection much faster. Then let's look at our experimental results. We tested AdaCluster on three mainstream video generation modules, Cog Video X2B, Hunyuan Video, and WAN 2.1, with NVIDIA A40 GPU. We have three key results. First, obvious speed improvement. Compared with original full attention, AdaCluster have a very greatly speed improvement. Second, nearly no quality drop. We use PSNR, SSIM, LPIPS, and other common evaluation metrics for testing. The results prove our methods only causes various line quality degradation. Third, great scalability. With increase of the token number, the running time of AdaCluster grows much slower than the other sparse attention methods. Finally, if you have any questions and need to contact us, please use the following WeChat and email address. Thank you all for listening.